Hi there, if you're sitting Maths A Level this summer, then this is the video for you. You are wanting to get the best grade you can, and you can't revise absolutely everything, so you have to think smart. There's no point spending time on the stuff you already know. You need to focus on areas of uncertainty. Now, in my videos, they will help you as they provide exam information, tips and tricks to use whilst completing the more trickier questions, as it's not the particular topic that pupils have not revised, it's the manipulation or the way that question has been asked that pupils find difficult. So completing as many past papers is the way to go. You should be practice applying your knowledge. So you can watch my solutions and then go away and practice. Okay, let's see what we've got in this video and get started. In the exam, you need to stay calm. There may be some questions in there that will throw you and make you think, and this may even be question 1. Up to 27% of the exam will require you to problem solve and apply your knowledge, and you will find these types of questions in all the past papers that you are working through. So you need to practice the skill and let your brain make those connections necessary to tackle that type of question. And if you are always relying on mark schemes, you will find this difficult in the exam. Now, in the exam, if you find that you just can't work a question, it's not coming out easy, just leave it out, because subconsciously your brain continues to think, and you may get a chance before the exam finishes to go back and rework that question. Don't give up on a question, as there'll be show that questions which are designed to help you. So if you've not been able to do part A and not get the show that part, then go on and max the marks for each of the questions and have a go at each of the parts. Okay, let's have a go and look at some questions. Okay, we're going to start by looking at a transformations of graph question, but it's also inside an integration question. What I've seen recently is the exam board incorporating 2 aspects of the syllabus into the same question and making you think, how does that affect, and in this case, the integration. So say in part A, we'd been asked to use the trapezium rule to estimate the area under a curve between 0 and 2, and the answer we got was 3.84. Now, everybody likes using the trapezium rule because you get the rule on the formula sheet, and if you know what you're doing, if you've done the revision, then that's a straightforward question, easy marks for you to get. But then in part B, they've asked us about the area or what effect it will have on our answer when we've got the same f of x, but we've got a plus 4 here. So we need to recognize that that is f of x plus 4, and this plus 4 is going to translate the graph 0, 4. The whole graph is going to shift up 4 places. So our new graph will still have the 3.84. That will be sitting there, our area, and it's all shifted up 4 places. We're still going between 0 and 2. So what we will have to add on to our 3.84 answer is the 4 by 2 rectangle, which will be 8. So we'll be doing 3.84 plus 8, and our answer would be 11.84. Okay, so being prepared to just think about parts of the course and how they could be incorporated into different areas of the course, into different contexts. So what if I was also asked to find the integral between 0 and 2 of 3f of x, and then maybe the add 4, or maybe even add 2. So the 3 on the front here is going to stretch the graph in the y direction. All the y coordinates would be times by 3, and this time, because we've got an add 2, it's going to translate the graph just 0, 2. So what effect would that have on our 3.84? We'd be doing 3 times 3.84 and then add on, this time, a 2 by 2 rectangle, so adding on 4. In this next question, I can see I'm going to be differentiating, and the function has got a numerator and a denominator that both involve the variable x. I'm going to be using the quotient rule. Now you don't get the product rule in the formula sheet, but you do get the quotient rule, so I've copied it here. The product rule is first differential of second plus second differential of first. So it starts with first and it's got a plus in it. And you learn to multiply first, so that's how I remember that. The quotient rule starts with bottom diff top and it's got a minus in it, top diff bottom, all over bottom squared, where the top is the numerator, that's going to be f of x, x minus 4 in our case, and g of x is the denominator, which is going to be 2 plus root x. Now I know I'm going to be differentiating, so instead of writing root x is the same as x to the half, so I'm going to be writing it in that form. So let's have a go at the differentiation. dy by dx is bottom, which is 2 plus x to the half, times the differential of top, which is just 1. Take away the top, which is x minus 4, differential of bottom. Now the 2 is going to go out. When we differentiate x to the half, we're going to power down and take 1 off. So that's going to be half x to the minus a half. And I've just written that in front so that it's easier to multiply it into that bracket. And then we're going to divide by the bottom squared, which is 2 plus x to the half all squared. Okay, so we need to multiply this term into the bracket. So when I'm multiplying x to the minus a half times x to the minus a half times x, and it would be x to the 1, you add the indices. So minus 1 plus a whole 1 is going to be a half. So that numerator is going to be 2 plus a whole x to the half minus half x to the half. And then the 2 and the 4 are going to cancel. This minus and this minus is going to make a plus, and it will be 2x to the minus a half. Now instead of putting that denominator underneath, I'm going to write it just next door as a division, and I need to do 2 plus x to the half all squared. So I'm going to write it out and times it by itself. Now I've got a whole x to the half here minus half of the same term. So collecting like terms, you're going to have 2 plus half x to the half plus 2, and then this x to the minus a half. That means that this x will go underneath, so it'll be plus 2 over x to the half. It's just the x that goes underneath, the 2 will stay on the top, and it's all of that divided by, now multiplying out this bracket, we've got 2 times 2, 4. The outers and the inners are going to be the same term, 2 lots of x to the half plus another 2, so that's plus 4x to the half, and then x to the half times by itself is x to the half times x to the half. Again, we're going to add the indices, so that's plus x. Now what I need to do is make this first term have a common denominator of the 2x to the half, so I need to have 2x to the half. So I need to multiply each of the terms here by that common denominator. So when we multiply the first term, we're going to get 4x to the half. When we multiply the second term, the 2's are going to cancel, and the x to the half times by itself is just going to be plus x. And then when we multiply the next one, the x to the half on the top is going to cancel, and we're just going to get plus 4, and that's going to be divided by the 4 plus 4x to the half plus x. And now we can see what's going to happen when we have a fraction divided by something. We're going to use keep, flip, change, KFC. You're going to divide and turn that term upside down. So we're going to have 4x to the half plus x plus 4 all over 2x to the half times 1 over 4 plus 4x to the half plus x. And we can see we've got exactly the same term top and bottom, so they can cancel. So this will be 1 over 2. Now x to the half is root x, so we can see I've now got it in the form that I've been looking for, and my a is equal to 2. Next, we've got everyone's favourite. Oh, do we all love a proof question? Not really, but part 1 of this one is okay and part 2 is a little bit tricky. So let's have a look at part 1 first. Prove that the sum of the squares of 2 consecutive odd integers is always 2 more than a multiple of 8. Well, 2 consecutive odd integers, we're going to call them 2n minus 1, and we're squaring them and we need to sum them. So we're calling the next one 2n plus 1. So squaring those out, you're going to get a 4n squared minus 4n plus 1. And then the other one squared out, 4n squared plus 4n plus 1. So this all adds to 8n squared. The 4n's will cancel and we'll have plus 2. And this is going to be 8 times anything is going to be a multiple of 8. So 8n squared is a multiple of 8. So 8n squared plus 2 is 2 more. So that is part 1. Part 2, prove by contradiction. So whenever you're doing a contradiction, you have to negate whatever is being said and then prove that what you've assumed is wrong, and that's your contradiction. So we're going to assume that log to base 2 of 5 is rational. So we're going to prove the opposite. So if log to base 2 of 5 is rational, then log to base 2 of 5 equals some fraction. You can call it m over n, p over q. I think I'll go with a over b, where a and b are integers. So you could say integers, the sign for integers is that Z sign, and a and b, the fraction there is in its simplest form. So how do we rewrite logs? We can say 2 to this a over b is equal to 5. Remember, 4 cubed is equal to 64. Another way to write that is log to base 4 of 64 is equal to 3. So 4 cubed is equal to 64. That pattern is how logs work. So we can say 2 to the a over b is equal to 5. Now what we can do here is raise both sides to the b. What you do to one side, you do to the other. These b's would cancel, so we'd have 2 to the a is equal to 5 to the b. Now 2 to the a, 2 to any power you like. If a is an integer, this is going to be even, and 5 to the b is equal to an odd. All your powers of 5 are all odd if b is an integer. So they do not equal, an even number cannot equal an odd number. So that's where we've got the contradiction. And therefore we can just say that log to base 2 of 5 must be irrational. In this question, we're asked to integrate and show that the answer is independent of a. So that means our answer has got no k in it. So we are integrating between k and 3k of 2 over 3x minus k. So this is the type of question where you're not going to bring that denominator up and say it's 3x minus k to the minus 1, because when we integrate, we add 1 on and divide by the new power. Dividing by 0 is going to cause us a problem. So this type of integration is where we're going to use ln's. So the 2 on the top is just going to join in. We're going to have the ln of 3x minus k, and then we're going to think about if we differentiate, it'll give us 2 over the 3x minus k, but when we differentiate using the chain rule, we'll then be times it by the differential of the inside function, which will give us another 3. So we need to compensate for that and divide by 3. So that'll be our answer for the integration. Now we'll put our limits on the end of our big square brackets, and then we're going to substitute those limits in. So what I can do is take 2/3 out and then put the 3k in. So it's the ln of, if x is 3k, it's going to be 3 times 3k, so that's 9k minus k, which is 8k. And then the other limit in, when x is k, it's going to be 3k minus k, which is 2k. So that's equal to 2/3 the ln of 8k over 2k. Using our log laws, the k's will cancel, and so overall the answer is 2/3 the ln of 4, and we can see it is independent of k. In part B, we're being asked to show that this integral is inversely proportional to k. Now, if m was inversely proportional to k, I would write it like that. And to get rid of the proportionality sign, I would write m is equal to some constant, let's call it c, over k. So when things are inversely proportional, as one goes up, the other goes down. So this sort of format is the answer we're trying to get, where the sum constant times by 1 over k. So let's have a look at the integration. We're going from k to 2k. Now this variable is in the denominator, and I've got a minus 2 on that bracket. Now I can write that as 2x minus k to the minus 2, and when I integrate with respect to that minus 2, I'm going to be adding 1 on and getting minus 1 and dividing by the new power, and because that's minus 1, it's not going to cause me a problem. So I'm going to write this integral as 2 into 2x minus k to the minus 2. And now doing the integration, the 2 on the front is just going to join in. I'm going to integrate with respect to the fact that it's minus 2, so that will be 2x minus k to the minus 1, divide by that new power. Now thinking about differentiating, when I power down and take 1 off, the minus 1 will come down and cancel with this minus 1 on the bottom, and I'll be taking 1 off and get back to that minus 2. But then I'll be differentiating with respect to the inside function, which will give me a times by 2. So I need to compensate for that and divide by 2. So those 2's will cancel. And then I'm going to write it in a form where this minus on the bottom I'll show on the top, and then this minus in the index means that that numerator is in the denominator, so 2x minus k, and I'm going between k and 2k. Now putting my limits in, putting the upper limit in first, it'll be minus 1 over, when x is 2k, you're going to get 4k minus 1k, which will be 3k. Minus, put the upper limit in, lower limit, sorry, it's minus 1 over 2k minus k, which will be k. Now this minus and this minus in the middle is going to give me a plus, so that's going to be 1 over k minus 1 over 3k. Now making 3k the common denominator, that's going to be 3 over 3k minus 1 over 3k, which is 3 minus 1, 2/3 over k. So now we've got it in the form where we've got a constant and that 1 over k, so we have actually done it. Next, I've got an integration by substitution. So when we're doing one of these, this is the substitution. We've got to substitute for all parts of the integral. So that is the limits, which are in terms of x, they need to go in terms of u. Everything in the integral in terms of x, and the dx. So don't let that dx throw you that it's there. It's usually there. It means the same thing, joining in with that 3. So let's get the dx on the go first. So dx by du is going to equal 2u. So what does dx stand for? Then we're just going to cross multiply. Dx is going to be 2u du. So I've done the dx bit. Now let's have a look at the limits. When x is equal to 10, because x is equal to u squared plus 1, 10 is equal to u squared plus 1. Take that plus 1 over. U squared is equal to 9, so u is equal to 3. When x is equal to 5, 5 would equal u squared plus 1. Take the plus 1 over again. 4 is equal to u squared, so u is equal to 4. Now, the substitution is that x is equal to u squared plus 1. So x minus 1 is equal to u squared. So I can see that is going to be u squared. And then x minus 1 square rooted is equal to u. So this part here is going to equal to u. So now I'm ready to do the substitution. I am going from 2 to 3 of 3 over u squared times 3 plus 2u, and then it's all multiplied by 2u du. So what's going to happen, that du on the end needs to be there in order for me to integrate, but these 2u can now join in with this algebra, so this u can cancel with one of the ones on the bottom. On the top you've got 3 times 2, which is going to give me 6, and then we've got u into 3 plus 2u du, and we're going from 2 to 3. So in this case, my p is 2, q is 3, and I've got my integral. In part B, we're being asked to go ahead and do the integration. It says hence, because we need to use the substitution that we found in part A, that this integral was equivalent to integrating between 2 and 3 of 6 over u into 3 plus 2u. So that's what we've got to do, and the answer to this will be the same as the answer to this, and we're trying to look for it in terms of ln of a, where a is a rational constant. Now, so we've got to recognize that this is a single fraction and we need to use partial fractions. So pulling out what we're integrating and splitting that up first, we've got 6 over u into 3 plus 2u. That's equivalent to a over u plus b over 3 plus 2u. Going clear of fractions and multiplying throughout by this denominator, both sides, we'll get 6 on the left, and that will mean on the right, the a and b terms will just get what they've not got in their denominator. So a will get the 3 plus 2u plus bu. Now we need to choose values of u that will make the a and b terms go out. So I'm going to let u equal 0, and then the b term will go out. So that will be 6 is equal to 3a. So that tells me that a is equal to 2. Now if I let u equal minus 3 over 2, the a term will go out. I'll still have a 6 on the left. I'll have minus 3 over 2b. Cross multiply, 6 times 2 is 12, divided by minus 3. That tells me that b is equal to minus 4. So I am integrating between 2 and 3, putting those constants back in. It's going to be 2 over u minus 4 over 3 plus 2u. Now, because the denominators are just single powers of u, that integrates to ln. So the 2 is just going to join in, ln of u for the first term, minus 4, the ln of 3 plus 2u, but then thinking about differentiating, that will go back in the denominator, but I will be timesing by the differential of the inside function, and I need to compensate for that by dividing by 2. So that is going to give me 2 in that second term, and we're going from 2 to 3. Now putting in my limits, I'm going to have 2 the ln of 3 minus 2 the ln of, when u is 3, 2 times 3 is 6, plus 3 is 9, minus, putting 2 in, 2 the ln of 2 minus 2 the ln of 4 plus 3 is 7. Now you can just use your log laws and do various ways. I might take a 2 out and then recognize that I've got an ln of 3 here, and this minus will make a plus. So doing the plus terms, it'll be ln of 3 plus 7 plus the ln of 7, and then we're going to have minus the ln of 9 minus the ln of 2. Using my log laws, it's going to be 2 the ln of 3 times 7, 21, divided by 9 times 2, 18, which is 2, the ln of cancelling down by 3, 7 over 6. Now you could leave it like that, but they want nothing on the front, they want that 2 to go up. So using your log laws, this is going to be the ln of 49 over 36. The first time an integration expressed as a limit of a sum question came up on an exam paper a few years ago, I was marking that paper and lots of pupils just got 0. They didn't recognise that when we've got this strip here, which is a thin strip, but it does have a width, delta x, as that delta x tends towards 0, it's going to be the same as just integrating between 2 and 5 of the cube root of x, which we're going to write as x to the third dx. So that's all you need to do when you have an integration question as a limit of a sum. So let's do the integration. We're going to add 1 on, so that'll be 4/3. Dividing by 4/3 is timesing by 3/4, and we're going between 2 and 5. Putting in our limits, it's going to be 3/4 times 5 to the 4/3. Take away the lower limit, 3/4 times 2 to the 4/3, and if you put that in your calculator, it comes to 4.5225, and they want the answer to 4 significant figures, 4.523. In this next question, I can see I'm going to be differentiating. I'm recognizing that I've got a product, so I need to use the product rule, but I haven't got y explicitly as the subject. I'm going to have to do implicit differentiation. So a lot going on. Let's have a go. When we're using the product rule, it's going to be first differential of second plus second differential of first. And when I do implicit differentiation, when I'm differentiating the tan y, I have to differentiate with respect to y, but then multiply by dy by dx. So we're going to have first differential of second, tan y is going to differentiate to sec squared y. Then because it was y, I then need to times by dy by dx, plus second differential of first, so it's going to be 2x tan y is equal to 0. Now I need to isolate that dy by dx and make that the subject. So dy by dx is going to equal, this term needs to go to the other side to be minus 2x tan y, and then I'm going to divide by x squared sec squared y. Now you can see where you're heading. You need to get rid of all the y's. So from my question, I can see that tan y is going to be 9 over x squared, and I will substitute in for that tan y in the numerator, and I can use the identity that tan squared y plus 1 is equal to sec squared y, and I will use this squared to go in there and replace the sec squared in the denominator. So this is going to be minus 2x times 9 over x squared divided by x squared times 81 over x to the 4 plus 1. So now this bracket, I'm going to make a common denominator, and I'll write it maybe next door to each other rather than a fraction and a fraction. I don't really like those. It's minus 18x over x squared divided by x squared. Now if I want to make that line go all the way across, I'll need to give that x to the 4 as well. So that will be x squared into 81 plus x to the 4 all over x to the 4. Now when we divide by fractions, we times and turn it upside down, use the reciprocal. So it's minus 18x over x squared times by x to the 4 over x squared into 81 plus x to the 4. Now these 2x squareds on the bottom will cancel with that x to the 4 on the top, and I've done it. It is minus 18x over x to the 4 plus 81. In part B, we're being asked to prove that there's a point of inflection on this curve at x equals the fourth root of 27. So let's have a little look at points of inflections. So away from this question, I'm just going to have a look at a cubic. And a cubic will have maybe a max and a min. And then if I graph the gradient function, when we equate dy by dx to equal to 0, that is finding, when we graph the gradient function, the roots of the quadratic. So this one's cubic, so when we differentiate we go down a power. This graph would be quadratic, and where this one has its max, that would be the root, and where this one has its min, that would be the root. Now if we have a look at the second derivative, that is differentiating the quadratic and going to give us just a linear, and where the first derivative has its min, that would be where the root is, and then we'd have a straight line. So where the cubic has a max, the second derivative is less than 0 because it's below the x-axis. When the cubic has a min, the second derivative is above 0. Now, where is the point of inflection? The point of inflection is where the gradient goes from slowing down to start speeding up. So if we look at the gradient function, it's getting lower, and then a point here where it's 0, and then it starts going back up. So this point of inflection would be here. So the graph, the gradient function, it's going slowing down, but then in order to approach that min, it needs to start speeding up. So this is where the graph goes from convex to here, concave to here, and then convex is the other side when the gradient function starts increasing. So what we're looking for a point of inflection is that the second derivative either side of the point of inflection is going to be a change of sign. So we need to show that we've got a point of inflection, so that is going to be the second derivative, so d2y by dx squared. Now we need to use the quotient rule, so that's going to be bottom times the differential of top, which is minus 18, minus the top minus 18x differential of the bottom, which is 4x cubed, all over the bottom squared, x to the 4 plus 81 all squared. Now these two terms are going to make x to the 4, so I've got x to the 4 plus 81 times minus 18. This minus and this minus will be a plus, and I'll have 18 times 4 times x to the 4, all over my x to the 4 plus 81 squared. Now when I feed in my fourth root of 27, when I'm going to raise that to the 4, they're going to cancel, so all the x to the 4s are just going to be 27. Now when you put 27 into that numerator, this first term here comes out to be minus 1944, and then we're plus the second term with x as the fourth root of 27 comes out to be 1944. So we can see the numerator is going to equal 0, so the second derivative equals 0 at x equals the fourth root of 27. So therefore we've got a point of inflection. Now if you do on your calculator what the fourth root of 27 is, it's 2 point something. So I could look at x is equal to 2, which would be the one side of the point of inflection, and x equals 3, and look for a change of sign. Now when you put those in, the second derivative at x equals 2 is going to be less than 0, and when x is equal to 3, the second derivative is above 0. So we have got a point of inflection. In this next question, I have got parametric equations. So I've got the third parameter t. I've got a point P on this curve C, where t is equal to 2. and we've got the line S, which is normal to C at P. For part A, we're being asked to find the equation of that straight line, which is the normal to the curve. So an equation of a straight line, we're going to need a point, which will be our P, and then we need the gradient of the curve, and we're going to do the negative reciprocal, and then use y minus y1 is equal to m into x minus x1. So first of all, finding P. So P is when t is equal to 2. So what is x when t is equal to 2? Subbing it into the parametric equation, 2 plus 1 is 3, and that squared is 9. And y is equal to 2 cubed, 8, half of that, 4 plus 3, 7. So this point P is the point 9, 7. So now we need to find the gradient. So we'll have to do parametric differentiation. So if we do dx by dt, that's going to give us power down and then times it by the differential of the bracket, which will just be 1. dy by dt is equal to 3 over 2t squared. Now make a chain. Dy by dx is going to be dy by dt times dt by dx. So that's going to equal 3 over 2t squared times, now I found dx by dt, so I'm going to have to put 1 over that, so that'll be 1 over 2 into t plus 1. So that's 3t squared over 4 into t plus 1. Now at t equals 2, dy by dx is equal to 2 squared is 4 times 3 is 12, and 2 plus 1 times by 4 is also 12. So the gradient of the curve at P is equal to 1. So the gradient of the normal will be minus 1. So now I've got my point of my gradient. I'm just going to do y minus y1 is equal to m into x minus x1. So y minus 7 is minus x minus 9. So y minus 7 is equal to minus x plus 9. So x plus y is equal to 16, just rearranging, and that is the equation of the normal. In part B, I have this region R bounded by the curve C, S and the x-axis and the line x equals 1. I'm going to use integration to find the area of R. Now, if we remember, this was the point where t is equal to 2 at P, and that gave us the x coordinate 9 and the y coordinate 7. So the equation of the line S was x plus y is equal to 16. Now what's happening here when I'm on the x-axis? Y is equal to 0, so that will be the point x equals 16. So this part of R is just a triangle, so I can do half base times height, which is going to be half times the base, which will be 7, and the height will be 7. So that's going to be 49 over 2. Now all I need to do is use integration to find this part of the area R, and that is the integral between 1 and 9. But because my curve is being given parametrically, I'm going to need to find what t is when x is equal to 1, because I need to do parametric integration. So when x is equal to 1, then we'll have 1 is equal to t plus 1 squared. So 1 is equal to t plus 1. So t is equal to 0. Now when x is equal to 9, I already know that t is equal to 2 there. So I'm going to be integrating between 0 and 2. Now when you're doing parametric integration, I can integrate y, but then I must times by dx by dt, and then I will be able to integrate with respect to t, because y is given in terms of t, and informally these will act as if they are cancelling, so I'm actually finding the integral with respect to x, but I'm going to do it all in terms of t. So between 0 and 2 of half t cubed plus 3 times the differential of x with respect to t, which is 2t plus 1, and then we're going dt. So let's sort this all out. We've got half t cubed plus 3, and then we've got 2t plus 2. So let's multiply out this bracket. So it's going to be half t cubed times 2t, so that will just be t to the 4 plus t cubed plus 6t plus 6. Haven't integrated yet. I'm still going between 0 and 2. So I now need to integrate t to the 5 over 5 plus t to the 4 over 4 plus 6t squared over 2 plus 6t. I'm going between 0 and 2. So when I put 2 in, I'm going to get a 32 over 5 plus 16 over 4, which is 4, plus the 6 and the 2 will cancel and give me 3 times 4, 12, plus another 12. And then we're going to have minus 0. Now that all comes out to give us 34.4, and then we add on the 49 over 2, the triangle, and it all comes out to give us 58.9. Now it did say in the question use integration to find the area, and I did the area of a triangle. So I suppose really we should have got this 49 over 2 by doing the integral between 9 and 16 of our straight line, which is y is equal to minus x plus 16. So if you'd done that with minus x plus 16 and integrated that, that would have given you the same answer, which added together gives you the 58.9. This next question is a max-min question. You would have learnt this in year 1, so just going over this because sometimes it gets forgotten about because you're doing all the harder stuff in year 2 and you might have forgotten to do this, and it's a nice question if you know what you're doing. So we've got the volume of the box, which is this thing here, is 300 centimeters cubed. Now we've got to show that the surface area is this expression here. Whenever you're doing a show that question, we're going to end up with this answer, and we've got to use the information along the way to get there. So the volume of this shape, which is a prism, the area of the cross section is a sector, so that's going to be half r squared theta times h is going to be our volume, and we're told in the question that that is 300. So we've got theta, the angle here, which is 1. So we're going to write half r squared h is equal to 300. Now noticing where we're going to, there's no h in the surface area. So that's how we need to use the information here to get h, the subject, which is going to be 600 over r squared. And we're going to substitute that into the surface area formula when we have a look at that. So part A, the surface area is going to be the top and the bottom of the box are both sectors, so we need 2 times half r squared theta, plus the sides and the other side here are both rectangles of RH, so we need 2 of them, 2RH, plus we need this rectangle here. So this is the arc length of the sector, and arc length is r theta, and this is h. So we need another r theta h, which is actually RH. So that's going to mean that we need 3 RHs. So the surface area is, we can cancel these 2's, r squared theta, and theta is 1, so that's r squared plus 3RH. And what was RH? From over here, it's going to be r squared plus 3r times h, which is 600 over r squared. The r's here will cancel, and it will get r squared plus 1800 over r. In part B, we're being asked to use calculus, which means we need to differentiate or integrate. We're looking for stationary points, so we're going to be differentiating. So we've got our formula for S, so we need to be doing ds by dr, but we need to write S in a form where that r is in the numerator position. So S is equal to r squared plus 1800 r to the minus 1. And now let's differentiate. Ds by dr is equal to 2r minus 1800 r to the minus 2, which is equal to 2r minus 1800 over r squared, and that's equal to 0 at the stationary point. So if we take the negative term to the other side, we're going to have 2r is equal to 1800 over r squared, cross multiply, 2r cubed is equal to 1800, r cubed is equal to 900, so r is equal to the cube root of 900, which is equal to 9.65 to 3SF. So in part C, we're asked to prove that this value of r gives a minimum, so we need to do the second derivative, so d2s by dr squared. So going back to the first derivative, which is here, and differentiating again, we're going to get 2 plus 3600 r to the minus 3, and then when r is equal to 9.65, the second derivative, if we put that value in, comes out to be 6.006, which is bigger than 0, so therefore we have a min. And in part D, it says find to the nearest centimetre squared the minimum value of S. So that just means put in that the R was 9.65 into the formula for S. So S is going to equal R squared 9.65 squared plus 1800 over the 9.65. If you do that on your calculator, that comes out to be 280 centimeters squared. Thanks so much for watching. I hope that the content has been useful. Please do give it a thumbs up and check out the channel for any other videos. Hoping they're helping and your revision is going well. Do check out my channel because I'm going to do a video on the changes the exam board have made to the textbook, and also I need to do some videos on the mechanics. I will also do a video once we've had Pure 1 on what we might think might be in Pure 2, which is the week later. Okay, thanks very much. See you on the next one.